Okay, I've defined the dot and cross products in 3 dimensions at least. Right here is a complete definition of the dot product. Right here is a complete definition of the cross product. Now, I'm not giving you a formula at this point for calculating the dot and cross products, but the formula follows from the definition, and the definition just comes down to the nature of the unit vectors. I'll try to explain some of that to you, but the calculation scheme, we're going to kind of focus on the calculation scheme for right now. Okay, so if you look here, I dot I is 1, J dot J is 1, K dot K is 1, and any other product is 0. So that it's going to turn out that when vectors are perpendicular, because I and J is perpendicular, I and K is perpendicular, the 0 products occur when you have perpendicular vectors. So if you have 2 vectors that are perpendicular, the dot product will be 0. So, perpendicular vectors the dot product is 0. If the vectors are parallel, it's going to turn out that the dot product is the product of the magnitudes. Now, I haven't proven that, but we can see that I has a magnitude of 1. When you dot it with itself, you get a magnitude of 1. Same with J, and same with K. And this follows from this and the Pythagorean theorem. I'm not going to prove it, but those are the 2 most important, maybe the most important. Okay, then the other is that the dot product of a vector v and a vector w equals the magnitude of v times the magnitude of w times cosine theta. Where theta is the angle between the 2 vectors. Okay, now I alluded to this in the preceding video. An example. Let V equal 2I plus 3J minus 4K. Let W equal negative I plus 2J plus 3K. Now, I haven't defined the way the operations work, but you have, for these vectors, the usual distributive law. The dot product distributes, meaning that V dot W is 2I, don't want to close that parenthesis, plus 3J minus 4K, dotted with negative I plus 2J plus 3K. That equals, by distributive law, 2I dotted with this whole vector plus 3J dotted with this whole vector minus 4K. dotted with the whole second vector. And that equals 2I times negative I, which is negative 2I dot I. And then 4 times I dot j, and 6I dot k. And I'm going to stop there for a minute and note that I dot I is 1, I dot j is 0, I dot k is 0. So this is just going to give us negative 2I. Okay? Because when the I, among I, j, and k, each of those vectors dotted with itself is 1, dotted with any of the other three, of the two others is 0. Okay, so this works out to just 2I. And then we have, I said plus, but you can have 3j times negative I, so it's minus 3j dot I. I said 3j times negative I. It's 3j dotted with negative I. We want to make sure we're using the right words. It didn't matter if it was plus or minus because j dot I is 0. This is going to give you 0 anyhow. So you can anticipate a little bit of this. And let's see, writing these things a little sloppily. But that's going to be plus 6 j dot j plus 9 j dot k. Well, this is going to be 0, and this is going to be 0 because you got a j dot I here and a j dot k here. The only thing you're going to have left is the 6j dot j, which is 6. And I wrote something carelessly here. Don't want to repeat it, so let's go back. 2I dot I dot I is 1. It's not I. So that's just 2 times 1. Negative 2 times 1. I left off my negative sign. Epidemic of carelessness going on in this basement here. Okay, so the negative 2I dot I gives you negative 2. Hopefully you noticed that. But since you're probably just trying to pick up the general gist of things, hopefully it didn't confuse you right then. Okay, now over here, again, we use the distributive law here. And we get a j dot I, which gives us 0. A j dot k, which gives us 0, and a j dot j, which gives us 1. J dot j being 1, this gives us just 6. And then on the k's, the same thing is going to happen. K dot I is going to be 0, so it doesn't matter what your coefficient comes out. The 4k times dotted with negative I is going to give you 0. K dot j is going to be 0, but k dot k is going to be 1. And we're going to then get 0 plus 0 plus 12 k dot k, careless again, minus 12 k dot k. So that's minus 12. Okay, and that equals, well, negative 14 and 6 is 8, negative 8. Now, usually we don't go to all this trouble with the distributive law and everything, but I'm going to ask you to write it out for a couple of problems to convince yourself. Really, all we get is we just match up the I with the I, the J with the J, and the K with the K, because anything else, when it's matched up, is going to give you 0. I mean, this is multiplied by this, and this is and multiplied by this as well, but they give you 0. The only ones that don't give you 0 are the 2I dot negative I, the 3J dot 2J, and the negative 4K dot 3K. 2I dot negative I, well, I dot negative I is, well, it's negative 2 times I dot I. which is negative 2 times 1, just negative 2. So you just look at what's in front of the I. A 2 here, a negative 1 here, you multiply them, you get negative 2. Boy, this is easy. A 3 here, a 2 here, j dot j is 1. So you get 3 times 2, which is 6, times 1, which is just 6. And negative 4k, and dotted with 3k is negative 12, k dot k, which is just negative 12 times 1, negative 12. You add them all up, you get negative 8, and there's your dot product. Now, when you work your assignments, when you read your section, you might not even see the distributive law. But if we want to understand how certain things work, we need it. And it's not a magical law that just gets sent down from on high. It's got a reason. It comes back to perpendiculars have dot product of 0, parallel vectors have dot product. A dot product's a product of their magnitudes. And that's the properties that we have here. Everything about dot products follows from this. There are other derivations of dot products, very good derivations. If you had a really good pre-calculus course, which nobody ever offers anymore, you would have seen it. Okay. Now we can do something very similar with the cross product. Now the cross product has the property, number one, that vectors, parallel vectors give you the zero vector. Also, the cross product always gives you a vector. These are just numbers. Cross product is a vector product, as it had better be if you want the cross product of this vector and this vector to be a vector instead of a number. So here it is. Now there's a calculation scheme using determinants and other ways to do it, but this is the way I'm going to define it, and the determinant calculation comes directly from this. Okay, so again, you see properties. When the vector is parallel to itself, as I is to itself, as j is to itself, as k is to itself, you get 0. And that extends to any pair of vectors in a way that's fairly easy to see once you understand this fact. The other is these vectors are all perpendicular, and the cross products of the ones that aren't 0 are all either the other ijk vectors or their negatives, so that the product of two unit vectors gives you a unit vector. Okay, maybe the unit vector is in the positive direction with its axis, maybe in the negative, but it's a unit vector. Okay, so the magnitude of I times the magnitude of j is equal to the magnitude of k. So when vectors are perpendicular, the magnitude of the cross product is equal to the product of the magnitudes of the vectors. So vectors are perpendicular, the cross product is 0. It inherits this property from these three facts. Okay? I said something a little bit over here. I'm going to put an absolute value sign around this dot product if you need that. Okay, but anyhow, with parallel vectors, don't worry about that. We'll come back and talk about it. But for parallel vectors, the magnitude of the cross product is the product of the magnitudes. Okay? Now I'm going to do a dot product of two vectors. I don't want to do v and w simply because it's going to get too long, because I've got three components of each. So what I'm going to do is I'm going to just take two components from each of these vectors. And maybe I don't want to call them v and w. Let's call them So like U and V, U, X, U, Y, U, Z. I'm going to say, I'm going to call the vectors S and T. And S is going to be 2I minus 4K. And I'm going to cross that with (2j) plus 3k. It's a shorter way to calculate these, although when both vectors are missing a component, sometimes it is quicker just to go back to the definitions. Okay, so that's going to be 2i cross 2j, and then it's going to be okay, 2i cross 2j, 2i cross 3k, and then minus 4k cross 2j, and minus 4j cross 3k. Okay, now there's a way to remember whether I and j give you k or negative k. But I'm not going to tell you right now. I'm just going to go back to the table. We'll talk about the right-hand rule. If you know the right-hand rule, it's obvious. Okay, 2i cross 2j is going to be, and I'm going to write it out, 4 times I cross j. 2i times 3k is 6 times I cross k. And here we're going to get negative 8k cross j and negative 12k cross k. And now you just got to know that I cross j is k. Now right-hand rule tells me I cross j is k. Okay? But that's easy, but I don't want to confuse you with it. As I said, if you know it, that's great. If you don't, we'll go over that. Or we'll just let the text and so forth give you that. So I cross k is negative j. K cross j is negative I. And k cross j is 0, so we have negative 12 times the 0 vector. I said it's 0. It's not 0. 0 is a number. It's the 0 vector. Okay? Well, if we put this in order, I, j, k, we're going to have 8i minus 6j plus 4k. If you sketch these vectors in 3 dimensions, or even model it with straws and a lump of putty or something, you'll see that the direction of this vector is very plausibly perpendicular to the direction of each of these vectors. Well, perpendicular to each, to the direction of each of these vectors. Okay? Also, the magnitude of S cross T is related to the magnitude of S and the magnitude of T. They just multiply those two magnitudes, and that's multiplied by the sine of the angle between the vectors. And I guess I better have the absolute value of the sine. Okay. Now one little caveat back here. I said the dot product is a product of the magnitudes. Well, no, dot products could be negative as they were here, and that's not a product of two magnitudes because the magnitudes are positive. The magnitude of the dot product, I put absolute value signs around them to give it a magnitude of the dot, to state that the magnitude of the dot product is the product of the magnitudes. So down here I can say that if the vectors are parallel. In general, the dot product is the magnitude of V times the magnitude of W times the cosine of the angle. And I don't have room to write that over here in the list, so I'll write it on the right. Okay. I'll say that V dot W equals the magnitude of V, which is easy to calculate from the Pythagorean theorem. We've got 4, 9, and 16, 29. Magnitude of V is the square root of 29, if I did that right, who knows. 1 and 4 is 5, and 3, and 9 is 14, so this is the square root of 14. You take the square root of 29 times the square root of 14, you get the magnitude of V times the magnitude of W. Okay, and if that's 29 and 14, 30 times 14 is 420, so 29 times 14 is 406, I think. Square root of 406 is about 20.3, no, about 20.15 maybe. So if you did the magnitude of V, or if you did the magnitude of V times the magnitude of W, you would get about 20.5. V dot W is negative 8. So the cosine of theta would be V dot W divided by the magnitude of V times the magnitude of W, which would be negative 8 divided by about 20.5, square root of 400, whatever I said. Okay, 406. So you could take the inverse cosine of that and find out what the angle is. Okay, and when you're viewing this, it's good to take that statement that I just gave you, which you're going to do dozens of times, and write it down if you understood what I was saying. So you really break the ice on these topics. So that's an introduction to the dot and cross products. You've seen how the cross product can be used here. The dot product can also be used to answer questions about that figure. But you already have enough information. I'm not going to ask you to do, I'm probably going to ask you to do one of the corners to get the cross product of the two vectors. So you can kind of verify that, yeah, that does appear to be perpendicular to the two edges. But I'm not going to ask you to do a lot of them this way. There's a determinate definition that you'll get drilled on through WebAssign and be explained in your text that I'm not going to bother with unless people have trouble with it, and people usually don't. But if you do, we'll take care of it. Okay. So, and there's a whole lot in this. What we're doing here is visualizing 3 dimensions, talking about vectors in 3 dimensions, and then talking about the dot and cross product, and even talking about planes a little bit, because that's what the first 5 sections of this chapter are. So I've kind of given you an introduction, a partial introduction. You can read the book, you can work through the WebAssign, and we'll, of course, have class where we maybe expand on these things a little bit.